This set of slides illustrates mean variance analysis. So a critical step in strategic asset allocation is the procedure we use for converting the inputs to a specific recommended strategic asset allocation. Much of the research by practitioners and academics alike has focused on developing and refining a variety of procedures. Many investment advisors apply judgment in making recommendations. We will be looking at the major procedures in use today, beginning with the most established, the mean variance approach. As with all approaches, mean variance should be subjected to professional judgment before adoption. So we'll start with the efficient frontier. According to mean variance theory, in determining a strategic asset allocation, an investor should choose from among the efficient portfolios consistent with that investor's risk tolerance. Efficient portfolios make efficient use of risk. They offer the maximum expected return for the level of variance or standard deviation of return. Efficient portfolios plot graphically on the efficient frontier, which is part of the minimum variance frontier. Each portfolio on the minimum variance frontier represents the portfolio with the smallest variance of return for its level of expected return. The graph of a minimum variance frontier has a turning point, which is the leftmost point, that represents the global minimum variance, or GMV portfolio. The GMV portfolio has the smallest variance of all minimum variance portfolios. The portion of the minimum variance frontier beginning with and continuing above the GMV portfolio is the efficient frontier. The standard deviation, which is the positive square root of variance, is used as it is easy to interpret. Once we've identified the efficient portfolio with the desired combination of expected return and variance, we must determine that portfolio's asset class weights. To do so, we use mean variance optimization. Here is a graph of the efficient frontier. The leftmost point is the global minimum variance portfolio. The line above that is known as the efficient frontier. It's the efficient set of portfolios. And on the graph, we do increasing standard deviation along the bottom axis and expected return among the vertical axis. Okay, so the unconstrained mean variance frontier. The simplest MVF optimization places no constraints on asset class weights, except that the weights sum to 1. In an unconstrained optimization, we only need to determine the weights of 2 minimum variance portfolios to know the weights of any other minimum variance portfolio. So here's an example. We have a minimum variance portfolio A, which has weights of 80%, 15%, and 5% to the asset classes within that portfolio, and it has an overall portfolio expected return of 10.5%. We have a minimum variance portfolio B, which has weights of 40, 40, and 20% to each asset class within that portfolio, with an expected return of 7.4%. To find the weights of the minimum variance portfolio with an expected return of 9.57%, we set up our equation where the one we need to find, 9.57%, is equal to the return of the first portfolio A, the weight of the first portfolio A, plus the return of portfolio B, multiplied by the weighting of portfolio B. Because they must both sum to 1, 1 minus the weight of the first one is equal to the weight of portfolio B. To solve for this, we expand out the bracket 1 minus W multiplied by 7.4 to get 7.4 minus 7.4 times W, and we solve for W. So we find that the weight of portfolio A is 70% and B is 30%. Then, for each asset class, we use the 70% weighting for the asset classes within portfolio A, and the 30% weighting for the asset classes within portfolio B to take a weighted average of the asset classes' weights in the two minimum variance portfolios. Doing so gives us the weight of the asset class in the 9.57% expected return portfolio. So, portfolio A's weighting is 70%. It has within its portfolio weights of 80%, 15 and 5, so 18%, 15 and 5. Portfolio B, 30% weighting. Within portfolio B, its asset class weights are 40, 40 and 20. So we do the weighted average of asset class 1. So that's asset class 1 and asset class 1. For portfolio A and portfolio B, we get 68%. Asset class 2 is 15 and 40% in each portfolio, gives us 22.5%. And asset class 3 is 5% and 20% in each portfolio A and B, gives us 9.5%. When we add those two together, or those weights together to check, we get 100%. So to summarize, after determining the asset class weights and expected returns of two minimum variance portfolios, we took a desired expected return level of 9.57%, which we set equal to a weighted average of the expected returns on two portfolios. This equation had a unique solution, giving the two weights of 70% for A and 30% for B. We applied those two weights to the known asset class weights of the two minimum variance portfolios to find the weights of the 9.57% expected return portfolio, which gave us the three weights of 68%, 22.5% and 9.5%. With the signed constrained mean variance frontier, we constrain the optimization that the asset class weights be non-negative and they sum to 1. So the negative weights would imply that the asset class can be short sold. So when we say that they have to be non-negative, then we are saying that we can't short sell them. The structure that we're talking about here also applies when we place an upper limit on one or more asset class weights. So we can say that for real estate, we don't want it to be more than 20% of our portfolio weight. So you can put those constraints on each asset class. The constraint against short sales restricts the choice. By the nature of a sign constrained optimization, each asset class in the minimum variance portfolio is held in either positive weight or zero weight. But an asset class with a zero weight in one minimum variance portfolio may appear with a positive weight in another minimum variance portfolio at a different expected return level. That observation leads to the concept of corner portfolios. Adjacent corner portfolios define a segment of the minimum variance frontier within which 1. the portfolios hold identical assets, and 2. the rate of change of asset weights in moving from one portfolio to another is constant. As the minimum variance frontier passes through a corner portfolio, an asset weight either changes from 0 to positive or from positive to 0. The global minimum variance portfolio, however, is included as a corner portfolio irrespective of its asset weights. In sign-constrained optimization, the asset weights of any minimum variance portfolio are a positive linear combination of the corresponding weights in the two adjacent corner portfolios that bracket it in terms of expected return or the standard deviation of return. And this is the corner portfolio theorem. Corner portfolios are relatively few in number. Knowing the composition of corner portfolios allows us to compute the weights of any portfolio on the minimum variance frontier. So let's look at an example. Look at an example to illustrate these concepts. So this is a UK institutional investor. He's developing a strategic asset allocation among 6 asset classes: domestic UK equities, international equities excluding UK equities, domestic intermediate and long-term bonds, international bonds, and real estate. So the investor cannot sell securities short or by on margin. So this is the hypothetical inputs. These are the expected returns for each asset class, the standard deviation, and the correlation between the assets. The efficient frontier, based on expectations in the table, showed that 7 corner portfolios provide the information needed to trace the efficient frontier. And in the efficient frontier of the portfolio is relevant. Expected returns and standard deviations and Sharpe ratios, which is a measure of risk-adjusted performance, are reported using a 2% risk-free rate. So here we have our asset classes. This was UK equities. This is international equities excluding the UK equities. Bonds, long-term bonds, international bonds, and real estate. And they've run it through the optimization program. And they see that corner portfolio 1 is 100% invested in the highest expected return asset class, UK equities. So note that these are all sorted in order of descending expected return. So 100% invested in UK equities. As we move to corner portfolio 2, we find that it's mostly invested in UK equities and we have some allocation to real estate. And the level of expected return ranges from 10% to 8.86% when we move from corner portfolio 1 through to 2. So any efficient portfolio with expected return between that of corner portfolio 1, the 10%, and corner portfolio 2, 8.6%, will hold UK equities and real estate. Because an in-between portfolio would be a weighted average of corner portfolios 1 and 2. When we look at corner portfolio 3, it has still some weight to UK equities. Now it's weighting, and it still maintains some in real estate, and now it's added some to international equities excluding UK equities. So therefore any efficient portfolio with an expected return between that of 3 and 2, or between 8.86% and 8.35% expected return, will hold a combination of UK equities, international equities, and real estate. Corner portfolio 7 is the global mean variance portfolio and is always the last portfolio. And you can see here our standard deviations are 5, 6, 8, 9, 10, 11, and 15%. And these are plotted on the graph, and these are the corner portfolios with 5, 6, 8, 9, 10, 11, and 15%. And these are their, so that's the standard deviations, and these are their expected returns of 10 would be 8.86, 8.35, 7.94, 7.30, 6.13, and 5.33. So they're plotted on the efficient frontier. So here's another example. Suppose we want to find the composition of the efficient portfolio with an 8% expected return. So the first step is to identify the adjacent corner portfolios, and we when you look back at the table, you see it's between portfolios 3 and 4. Portfolio 3 has an 8.35% expected return and Portfolio 4 had a 7.94% expected return. As we saw in the previous example, this is our arithmetic. The one we want to find is 8%. It's equal to 8.35% expected return of the weights of Portfolio 1, which is corner portfolio 3, and 7.94% times the weight of corner portfolio 4. And when we solve that, we find the weight is 0.146 for 3 and 0.854 for corner portfolio 4. The 8.35% expected return corner portfolio has the weights, and when you look back at the table, it has the weights of 40.31%, 13.85%, 0.00, and 45.83%, multiplied by its weight that we just solved for, plus the weight of corner portfolio 4, which has the weights of 32.53, 14.3, 00, 8.74, and 44.64%. And when we multiply that out, an efficient portfolio with an 8% expected return will have weights of 33.67%, 14.23%, 00, 7.46%, and 44.64%. The 8% expected return efficient portfolio includes UK equities of 33.67%, international equities excluding UK of 14.23%, international bonds of 7.46%, and real estate of 44.64%. Intermediate and long-term bonds are not in the portfolio, they're the zero weights. Here's another example. So find the standard deviation of a return on the 8% expected return efficient portfolio. So identify the adjacent corner portfolios, which were 3 and 4, because the standard deviation lies between the 9.83% and 8.99% of corner portfolio 4. The second step is to find the portfolio weights using the returns of the adjacent portfolios. So the 8% is equal to 8.35 weighting portfolio 1 plus 7.94% the weighting of portfolio 2, and we've already found those weights. Step 3 is to get the weighted average of the two corner portfolio standard deviations, which is the weighting of portfolio 3 times its standard deviation plus the weighting of portfolio 4 times its standard deviation, and we get 9.1%. But the actual standard deviation will be slightly less because of the curvature of the efficient frontier, reflecting less than perfect positive correlation. So there are limitations to this approach. The recommended asset allocations are highly sensitive to small changes in the inputs and therefore to estimation error. It's estimated that a small increase in the expected return of one of the portfolio assets can force half of the assets from the portfolio. Thus, the expected return inputs are very important and often difficult to estimate. Investors should consider sensitivity analysis with an emphasis on the effects of different expected return estimates. That approach is ad hoc, however. It's possible to use resampled efficient frontiers, and these will be discussed in upcoming sets of slides, and always apply a professional judgment in evaluating results.